something new. Okay, I'd like to talk about chapter 7 of my book, which is on the green function.
Are you done with mode matching?
I'm not going to go into details. Okay. I'm just going to tell you the physics of it, and then the math you can figure that out. I think I told you the most important physics about mode matching, which is mode conversion. That if you have a single mode coming in, that mode sprays into a multitude of modes on both sides of the waveguide junction, or any discontinuity. Okay, and that is the only essential physics that comes about in mode matching. Of course, using this kind of technique, another essential thing is that you can reduce a three-dimensional problem into a series of two-dimensional problems, and it becomes a very popular technique in solving many optical waveguide problems and different kinds of microwave problems. Okay, I'm not going to go into detail because I went to do that in quite a bit of detail in the waveguide theory course. Okay, so I'm not going to go into that much more detail in this course. So I'm going to talk about the Uiuc-Green's function. And the Uiuc-Green's function, I think we learned that if we have an electric field, that you can write the electric field in this manner. Yes, I use it. Let's put a dot product here. Where G of R prime equals e to the I k naught R minus R prime over 4 pi R minus R prime. Okay? And we'll derive this in chapter 1 of the textbook. Okay? And hence it's very tempting to write the electric field in this manner, in a more succinct and compact manner, and write this as, take all this thing inside, and write this as the R prime. Put this as a diet because this is an outer product of two vectors. So that is a diet. This is just an identity diet. Hence, it's very tempting to write things like this. Where G now is defined as I plus del del over K naught squared G of R minus R prime. It's very tempting to write in this manner. But it turns out that it is wrong to write it in this manner. It's not correct to write it in this manner. And do you know the reason why? That we cannot write the electric field in this manner. What is the error that we have committed in expressing this in that form? Can anybody see an error that we have committed?
Absolute value will give you an R prime, so R prime cosine an angle, so if you take the divergence.
No? You mean there's something wrong with this one?
No, the expression contains both R and R prime.
We can change R and R prime. This thing doesn't change, right? So presumably I can exchange the order of integration and differentiation and put this piece in there and call this G, where I find G to be that. But there's an essential error that haven't been committed when we did this. Does anybody know what the error is? Well, the error is in that when you exchange the order of integration and differentiation, you have to be careful. Just like when you exchange the order of two summations to summation with an integral, you always have to be very careful. What do you check after that, after the exchange of the order?
Convergence.
You check convergence, right? It turns out that this is not allowed because this integral in there actually does not converge. Okay, because if you look at G, the singularity is on this order when R approaches R prime. So when the source and the observation point are very close to each other, there is a singularity there. And this one is double derivative. So you might have things like partial x squared, you might have partial x, partial y term, and other second derivative terms. So if you differentiate 1 over R once, you get 1 over R squared kind of thing. If you differentiate it 2 times, you get 1 over R cubed. Okay, plus some angular terms. And it turns out that this gives rise to a very singular integrand that does not converge. It does not converge because this thing is proportional to volume. The R is proportional to delta V. It's proportional to R cubed, perhaps we can say it's R squared dr, or R cubed kind of thing. Okay, so it's roughly R cubed, delta R cubed. Kind of thing. But even though this singularity seems to be annulled by this singularity, and yet this thing does not converge. It does not converge for the reason that it depends very much on how you perform the integration. You can get an integral out, but the integration value is not unique. So this gives rise to a lot of problems in writing it this way. So we have to be dealing with this in great care. Okay, we can actually also derive this expression using another approach. In chapter 1, we just used the vector wave equation to derive this, and then did a whole bunch of integration by parts to get that. But we can also derive the expression by using scalar and vector potential approach. Say if we use the fact that mu h is equal to curl of A, and it goes back to Maxwell's equation, so the curl of h is equal to I omega epsilon E, and the curl of E is I omega mu h. This is minus J, and this is J here. Oh, sorry, J is not there. J is here. Okay? So if you were to, there's many chunks on the floor. I don't know why. It's not my doing, somebody else's. Okay. I don't know why there's so many chunks. Okay, that is the case. Then if you plug into this equation, that mu h is curl of A, then this would give you I omega curl of A as a possibility. And this equation means that curl of E minus I omega A is equal to 0. It means that E minus I omega A must be the gradient of some potential of some sort. Okay, which means that E must be equal to minus grad phi plus I omega A. So we have two equations using the vector potential and the scalar potential approach. The E should be such. And then you can also derive a vector wave equation for, actually for curl of A. If you take this equation and you multiply by mu curl of H is curl of A, okay, is equal to minus I omega epsilon mu E plus mu J. So if you take this equation, multiply by mu, and then substitute that with the above to get this equation over here. Okay, and then you substitute the fact that E is given by this expression over here. So you get I omega mu epsilon phi with a plus sign out front, and then minus I times minus I, which is plus omega squared mu epsilon A plus mu J. So you get this as one of the equations. Did I get it?
Gradient of phi. The gradient of phi.
What?
I omega mu epsilon gradient of phi.
Gradient of phi, yeah. You're correct. Gradient of phi. Okay. Gradient of phi. There's still something wrong with this equation. Let me check.
We lost our friend epsilon.
Let me see. There's still something wrong here. I multiply by mu, I get this equation, and then I substitute mu h with curl of. So this is not there. Okay, this is not there. Because I substitute mu h with curl of a, so I get that. And then I should be okay right now, right? So curl of a minus k square a. K square is k naught square a. Must be equal to I omega mu gradient phi plus J. Okay? And then you use this substitution that this is gradient of divergence of A minus the Laplacian of A minus k squared of A equal to I omega mu gradient of phi mu J. Then you pick a gauge, what is commonly known as a gauge, to get this term to cancel this term. So you pick divergence of A to be equal to I omega mu phi. If you pick this to be this term, then these two terms cancel. And then the resultant equation you have is equal to minus mu J. Okay, there's one equation that you get. Another equation that you can get is by taking the divergence of this equation. From the divergence of E, in free space should be rho over epsilon, should be equal to minus the Laplacian of phi, and then plus I omega divergence of A. But we have picked divergence of A to be this one over here. So this becomes, if we multiply together, minus omega squared mu. This should be an epsilon something. Divergence of E is equal to rho over epsilon is Laplacian of phi. Is I omega divergence of A. I should have an epsilon somewhere.
The
previous line.
Yeah,
you
I
dropped
should
that
have an epsilon here. I should have an epsilon here. I should have an epsilon here. Yeah. You were correct that I missed out this one. I should have an epsilon here. I should have an epsilon here. Okay? And then I should have an epsilon here. And that's what I'm looking for. And I have the next equation. One of these equations is this one over here. The other equation is this one over here. So I have these two equations using the vector and the scalar potential approach. I know how to solve them because I know how to solve one of these equations. If I know the Green's function, there should be something over here. Okay. I know the Green's function of the system, which is that I know the fact that I know this to be true. Okay. I'm not keeping my k and k naught very consistent. Just think of those k's that I have over there, the same as this k naught over here. So I have this as my equation and solution. Then by the principle of linear superposition, I know that this has to be true. It has to be the convolution of this J of R prime. It must be the convolution of that because this is just, we can think of this as three scalar components xyz, and if you do xyz component independently, you get this equation. And then you also get this. There should be a mu here. 1 over epsilon. Okay, you can get the solution via the scalar and vector potential approach, and then you have your E. Your E is then given by this expression over here. So your E is equal to I omega A, but A is given by this expression over here. Okay, there should be no minus, because I put a minus here, minus here, minus here. It should be plus here. Okay, sorry about that. So this is just I omega A. Okay, if I take I omega A and substitute A with this, I get that expression over there. And the second term is minus grad phi. If you substitute that in properly, I should get minus grad of dr prime g of r prime g of r prime. Okay. So this is no, sorry, charge. This should be charge. Right? So this should be correct, right? Didn't make any mistake, no mistake so far, right? This should be correct. And this is derived using the scalar and vector potential approach. Okay, this is just minus grad phi, where I substitute phi from here. Oh, sorry, this should be rho. Okay, this should be rho. So this is obtained by solving this equation. So this must be correct. But we know that divergence of J is equal to I omega rho. Okay, this is from the continuity equation. Hence, we can also substitute that rho r prime is equal to divergence prime of J of r prime. I omega. And hence we can write this equation as I omega mu with the first term minus gradient of I omega epsilon dr prime g of r prime. And then that one I can replace with divergent prime of J of r prime. So this is correct so far, right? So this expression has no problem in terms of evaluation, because this is 1 over r singularity, this is charge, and this integral has no problem of convergence, because this will have an r cubed coming out from it. This is 1 over r. And there's no convergence issue with this. Okay? The convergence issue comes only if you do integration by parts. Let this operate on this, and then further on, take this outside the integrand. Or if you put them both inside the integrand, both this inside, and let this operate on that, then you get this 1 over r cubed from. So the thing is that if you have something like this, then you can do something like this, which is that you break this integration into V. You break the integration over V. If you have any source J of R prime that is occupying a volume V, you can break this into V minus delta V plus delta V. You can break that into two parts in such a manner. So you start to integrate, like if your observation point happens to be inside here, okay, you put a delta V called the exclusion volume around, and outside will be just V minus delta V. And this is called the exclusion volume. Okay. If you do this, then you can actually break this integration into two parts then. You can break this integration into two parts. J of R prime. And then first integrate outside that region, or just outside the exclusion volume, and this integral will always converge. Okay, then you can have integration just on the exclusion volume alone. Yes, you have a question? Somebody had a question? No? Or somebody stopped outside. Okay. So you can break that integral, this integral, into two parts. And the first one will always converge because I never include the singularity. The second one, well, would also converge because this is 1 over R singularity. Okay? So, and it turns out that, let me say this. It turns out that because this always converge, I can actually do integration by parts now and let this delta prime operating on G. Okay, so I can say V minus delta V, let me call it I. Okay, just concentrate on this integral I. Okay, I can let the integration by parts happen and say that I is equal to the R prime gradient prime of G of R prime dot J of R prime plus the second part. Okay, second part. Do you want me to do the integration by parts carefully? Essentially, in integration by parts, what you do is to write this as the divergence. Okay, actually I didn't do it very carefully, so it was my fault. I should write this as a divergence of Gj. Okay, I should write this as the divergence of Gj. So I didn't do it very carefully. So if I use the fact that divergence prime of G of J R prime, this should be equal to gradient prime of G dot with J of R prime plus G divergence prime of J of R prime, which means that this term over here can be replaced with a negative distance plus a divergence term. But then when I integrate this over v minus delta v, okay, I will get the surface term coming from this. Okay, I will get a surface term coming from this. So I have to actually keep the surface term. Okay? The surface term will have two surfaces. Because v minus delta v is bounded by this surface, okay, which I will call delta S, plus this outer surface over here, which I will call S. Okay? So this would have two integrals when I integrate over the surface, because I can use Gauss divergence theorem and convert this into a surface integral. I will have two terms now. Then I do a trick. I do a trick that I'm going to make V slightly larger than the volume that supports the current. Okay, I'm going to make V slightly larger than the volume that supports the current. When I integrate this over V, I make this V slightly larger than the volume that supports the current. Then on that surface, this surface, the larger surface of the two, J is always equal to 0. Okay? Even though this converts into a surface integral, J of R prime ds, where S is the larger surface plus the smaller surface, this will convert to that. The larger surface always gives me 0 contribution because I make a trick. Then I pick the larger surface to be slightly larger than the support of the current, and the current is always 0 there. So I'm only left with a smaller surface. So if I were to do this correctly, okay, I should be equal to this term J of R prime, okay, plus the surface term, but only the surface contribution from the smaller surface, not the larger surface. This should be the S prime, N prime dot G R R prime dot J of R. Okay, so only the contribution from the smaller surface.
What allows us to do that? Making the volume slightly larger.
I can pick the volume when I do this integral. I can pick my volume to be larger than the support of the current. There's nothing to stop me from doing that, right? I define this volume to be larger than the support of the current. So the current might be supported on this volume. I just pick my volume slightly larger. The outer surface will always disappear. Right? There's no reason to, nothing to prevent me from doing that. And then plus this integration over the smaller volume term. I'm claiming that this term is going to be 0 if I make delta V very small. So limit of delta V tends to 0, this thing goes to 0. Why? Because this is a 1 over R. This is a R cube. This is finite. These are charges. They are finite quantities. So if I make delta V very small, so in the limit that delta V becomes very small, this goes away. Okay? But it turns out that this term wouldn't go away. This term is the, no matter how small you make your volume, that term wouldn't go away. What is the physical meaning of this term? The physical meaning of this term is that you have some current J, okay, flowing in this delta V, and then the J is suddenly been truncated. Because the J is suddenly been truncated, it will be charges built up on this small delta V that you have. And n dot j is the kind of the few charges due to the discontinuity in the current. And these charges would always be there, and they contribute to a potential at your observation point, no matter how small you make this cavity. No matter how small you make this cavity. Moreover, this term depends on the shape of the cavity. If you have a cavity of this shape, if you put your observation point in there, that is what we are doing over here, you will get a different value for this term. And it is always there irrespective of how small you make your cavity and how small you make your exclusion volume. Okay? So finally, this term is always there. And as you make things very small, it only depends on the local value of the current about that point, plus this integration, which depends on the shape of the exclusion volume. Okay? And the first term, I can change this into minus gradient of G of R prime, just by changing the variable. This was operating on the prime variable. If I make it operate on the R variable, it just becomes minus del. And I can take the two del's outside. So after some manipulation, I can take this del outside. But what I'm left with is this term hanging in there. But then when I take the two del outside, the first term is defined with an exclusion volume. Okay? So finally, what you get is that you can write it in that form that we had started out with in the beginning of the course, but we have to say that ER is something of this form. I omega mu, because I take these two terms outside and combine the two terms, and then I get something that looks like my dyadic Green's function. Limit of delta V goes to 0, the exclusion volume goes to 0, dr prime over V, and then I combine these two terms together. I take this del outside, okay? I combine the two terms together. I would have, the first term is just I, okay, the first term is just I dot J. The second term is my del K squared. And then I would have this minus delta V before this integral is well defined. This first integral is well defined now. Okay, if I put a small exclusion volume, then I can take the del operator outside, and the first integral will be well defined. And it's just combining this term. But I'm left with this residual term. This residual term is the integration over the small exclusion volume. It depends on the value of J, right? At where that J is. So I can actually write the second term, this term that is left over, as a tensor times J at R prime divided by I omega epsilon. Okay, I can always write the effect of this term. So that is the correct way to write this dyadic Green's function. And one should never write it in this manner. This manner is wrong. This manner is wrong if R and R prime are both in the source region. Okay, so this is actually wrong to do it this way. If R and R prime coincide. If R and R prime coincide, we should write it in this manner. And you can think of the first integration as some kind of a principal volume integration. The dyadic Green's function times j of r prime plus a residual term, okay, which I can write as L dot j of r prime, not r prime, r divided by I omega epsilon. So this is the correct way. This is the correct way to write the Darling-Green's function. And so you can think of this principal value integration like what you have experienced in one dimension in complex variables course. You also have a principal value integration. But this is 3D. There's something very unique about this. This is dependent on the shape of the exclusion volume. If you pick a different shape, you get a different answer, because this integral that you have here finally depends on the shape of the exclusion volume.
But why are we using the concept of an exclusion volume in the first place?
Oh, because that integral did not converge. Remember?
Yeah.
That integral, if we let both the del operator operating on G, that integral does not converge. But if we do a small exclusion volume, then we can come up with an integral where both del can operate on G and this integral still converges. Okay? But in order to have this in this manner, you have to keep track of the surface integration term. The surface integration term. And that surface integration term means that there is a surface charge on the wall of this cavity or this exclusion volume that you have. And those surface charges are contributing to the field at the observation.